In Lesson 8, we're going to look at complex numbers and the complex number system. The complex number whose square root is -1, that is, the square root of -1, is I. And we know that I squared is defined to be -1. Any number that's in the form of a plus bi is said to be an imaginary number. A is the real number part, and b is the imaginary part. A complex number is the set of real numbers plus the set of imaginary numbers. And a pure imaginary number, let's say we have the number a plus bi, that's a pure imaginary number if there's no real number part, but there is an imaginary part. In that case, a pure imaginary number would be in the form of bi. We can graph imaginary numbers by using the complex number plane. A complex number plane is a plane that's similar to the coordinate plane that we use to plot complex numbers. The ordered pair a, b represents the complex number a plus bi. So the horizontal axis is the real axis, and the vertical axis would be the imaginary axis. Next, we see that an absolute value of a complex number is denoted by absolute value bars a plus bi. And to find the absolute value of a complex number, we do a squared plus b squared, find that sum, and take the square root. Complex conjugates are anytime we have an imaginary complex number a plus bi and its conjugate a minus bi. In example 1, we see the definition of the square root of a negative number. This is the imaginary part, the -1. So by definition, the square root of -1 is I, and we take care of that first. So real numbers, we have real numbers like 7 or pi or square root of 2 or 3.5. Those are real numbers. But we have imaginary numbers such as 2 plus 5i or 3 minus I. And then we have pure imaginary numbers when we have things like 2i or -5i. When we graph imaginary numbers, the real part is the x-axis. So the real part is the real number, and the imaginary part is the complex or y-axis. So if we wanted to graph 2 plus 3i, we would come over to 2 on the real axis and go up 3 on the imaginary axis, and that point would be the representation for the graph of that complex number. So 4 minus 3i would be located 4 units right and 3 units down. This would be complex number b, and 2i would be on the y-axis, the imaginary axis, and then -1 plus 0i, that would be on the real number axis. In example 3, we want to use the properties of complex numbers and simplify some expressions. So first we want to take care of the -1 part, since that's the imaginary part, and then I want to break 12 down into a perfect square root of 4 times the square root of 3. So in simplified form, the square root of -12 would be 2i square roots of 3. The square root of 25, -25, would be -1 under the radical times the square root of 25. So first the complex part, imaginary number, and then the square root of 25, the square root of 25 is 5. But we don't want to leave it in that form, I times 5. We want to put the I at the end because that's common notation. And here again, we're going to take care of the square root of -1 first, and then the square root of 7. So this is I times the square root of 7. Now in this particular case, different from the example in B, I do want to leave the I in front, because if you write 7 under the radical and then put the I, sometimes you don't know that the I is outside of the radical. So it's best to leave the I in the front and the radical last. Part D says to explain why negative square root of 64, or the square root of -64, is not the same as -1 times the square root of 64. So we can do that fairly easily. So -1 times the square root of 64 is 8i. But negative times the square root of 64 is just -8. Those are not the same. Example 4, we want to graph the absolute value of each complex number. So thinking about the graph of 2 minus I, if we go 2 units right and 1 unit down, that dot, or that point right there, is the representation of the letter A. Now if you think about the distance here, we're going 2 units right and 1 unit down, so the length of the hypotenuse, that's going to be our absolute value. And the definition said the absolute value of 2 minus I is the square root of A squared plus the square root of B squared. So that would be 4 plus 1, or the square root of 5. So the absolute value is the length of the hypotenuse here, that little red hypotenuse. For letter B, the absolute value of -3 minus 2i is going to be this length here, which is the square root of A squared plus B squared, and that would be 9 plus 4 under the radical. So the absolute value is square root of 13. For part C, 1 plus 4i is located right here, and we're trying to figure out the hypotenuse there, since that's the definition of absolute value. And we're going to calculate A squared plus B squared, which is 16 plus 1. So the absolute value is the square root of 17. And then finally on part D, we want 3i, and just by inspection you can tell that the absolute value is just the length of that y-axis from the origin, so the absolute value is 3. So we can simplify, we can graph complex numbers, we can find the absolute value, and we can also add and subtract complex numbers. To add and subtract a complex number, we want to add the real part to the real part and the imaginary part to the imaginary part. In this case, 7 minus 3 would be the real part, and -2i plus I would be the imaginary part. So 4 minus I is the simplified sum of those two complex numbers. In letter B, we have 1 plus 5i minus 3 minus -2i. So let's add 1 minus 3 and 5i plus 2i. So we're ending up with the real part, -2, plus 7i. We always write the real part first and the imaginary part second to be in standard form. In part C, we have 8 plus 6i minus 8 minus -6i. So the 8 minus 8 for the real part is 0, and the 6i plus 6i gives us 12i for the imaginary part, And in this case, we have a pure imaginary number, 12i. Finally, in letter D, we have negative 3 plus 9i plus negative 3 plus 9i. So the real part is negative 6, and the imaginary part is 18i. So negative 6 plus 18i. For example 6, we're going to multiply complex numbers and simplify. So 7i times 3i is 21i squared. But our vocabulary told us that I squared is defined as negative 1, so 21i squared can be simplified to negative 21. Here we want to use distributive property twice, so letter B, 2 times 4 is 8, and 2 times 5i is 10i. Negative 3i times 4 is negative 12i, and negative 3i times 5i is negative 15i squared. So we can add 8, and 10i minus 12i gives us negative 2i, but the negative 15, again with the I squared by definition, as negative 1, we find that we can simplify the 8 minus 2i plus 15, and that's going to give us 23 for the real part and minus 2i for the imaginary part. In part C, we're multiplying conjugate pairs. Negative 4 times negative 4 is 16. Negative 4 times negative 5i is positive 20i. 5i times negative 4 is negative 20i. And 5i times negative 5i is negative 25i squared. But there we have that I squared again. So we have 16 plus 0 minus 25 times negative 1, and that's 16 plus 25. So an interesting feature is when you multiply conjugate pairs, your answer is a constant. And here we're going to recognize the patterns for complex numbers, or powers of I should say. So we already know that I is just the square root of negative 1 by definition, and I squared is the square root of negative 1 times the square root of negative 1, which is negative 1. So I cubed can be rewritten to be I squared times I, and I squared times I would be negative 1 times I, so negative I. Then I to the fourth power can be written as I squared times I squared, which is negative 1 times negative 1. That becomes positive 1. And then I to the fifth, I want to rewrite that as I to the fourth times I, and I to the fourth is 1, so 1 times I is I. And then I to the sixth can be written as I to the fourth times I to the second, which is 1 times negative 1, so we have negative 1 again. And what we've done is developed a pattern here. So the pattern changes every fourth power. We have I, negative 1, negative I, positive 1, and then it starts to repeat. I, negative 1, negative I, positive 1, and so forth. In example 7, we want to use division for complex numbers, and the way we divide complex numbers is we rationalize the denominator. And by rationalizing the denominator, I want to think of the conjugate of 5 plus 4i, which is 5 minus 4i, since that's going to give us an integer. And we saw that when we multiplied. So I'm going to write 5 minus 4i as a form of 1 here. This is the number 1. And we're going to multiply the numerator and the denominator by this well-chosen 1. So our numerator becomes 25 minus 20i minus 20i plus 16i squared. And then we have 25 minus 20i plus 20i minus 16i squared. Simplifying the numerator, we have 25 minus 40i minus 16, because this becomes 16 times negative 1. In the denominator, we have 25, and then the middle I terms disappear because we had conjugate pairs here. And then the minus 16i squared becomes plus 16 with the definition of I squared. So in our numerator, we have 25 minus 16, and that's 9 minus 40i. But in the denominator, we have 25 plus 16, and that's 41. Now, oftentimes, we'll rewrite this to be in complex number form. So the proper form would be 9 over 41 minus 40 over 41i. So that's the proper way to write our result. In letter B, we want the conjugate of 6i to be our well-chosen 1. So that would be negative 6i over negative 6i. And multiplying through on our numerator, we have negative 24i plus 6i squared. And in the denominator, we have negative 36i squared. And once again, this is going to become negative 6, and this is going to become positive 36. So in our numerator, we have negative 6 minus 24i. In the bottom, we have positive 36. So if we factor out a negative 6 from the top, that would leave us with 1 plus 4i. And 36 on the bottom, we can remove a 6 from the top and the bottom. And then in simplest form, we have negative 1 over 6 minus 2/3 I, since 4 over 6, this 4 here and this 6 here would reduce to 2/3. And then finally in part C, again, we need the conjugate pair of the denominator, which is going to be 3 minus 4i. So we need the well-chosen 1, 3 minus 4i divided by 3 minus 4i. And then using distributive property twice, 5 times 3, 5 times negative 4i, negative 2i times 3, and negative 2i times negative 4i is positive 8i squared. So 8i squared. In our denominator, we have 3 times 3, that's 9. 3 times negative 4, that's negative 12i. 4i times 3, that's positive 12i. And 4i times 4i, that's negative 16i squared. Here we're going to have minus 8. And down here we're going to have plus 16. And the I terms would eliminate. So we have 15 minus 26i minus 8. And then we have 9 plus 16. So 15 minus 8 leaves us with 7 minus 26i in the numerator and 25 in the denominator. and then simplifying into a complex number, the real number part plus the imaginary part, 7 over 25 and 26 over 25. And we have finished Lesson 8 in Unit 4.